Okay, so we just talked about addition and scalar multiplication. Okay, and when we have these ideas in mind, okay, we are now able to represent all vectors in terms of something called a basis. Okay. Basis vectors. Okay. And these have a special name, which we'll talk about in a little while, but the basic idea here is very simple. Okay, so we saw that if I have a vector, say a simple vector here, let's say 3 and 4. Okay, this vector can it can have scalar multiplications, and it can have additions. Okay, so one of the ways that I'm allowed to represent this vector would be that I could have this as 3 times the vector 1, 0, plus 4 times the vector 0, 1. Okay, and let's see what would happen when I do that. Okay, well, I would have 3 times 1, which is 3, and I would have 3 times 0, which is of course 0. And then I could have that be 4 times 0, which is of course 0, and 4 times 1, which is 4. And then I end up with my answer when I add both of those together, because 3 plus 0 is 3, 0 plus 4 is 4, exactly as I have. Okay, so this vector here, 1, 0, and 0, 1, these allow me to represent any vector, basically, in terms of 1, 0, and 0, 1, if I break it up in this way. So for example, say I take 7 times 1, 0, and I have plus, we'll make it 5 times 0, 1. Okay, well, this is fairly straightforward. This would be 7 times 1, and 7 times 0 is 0. Then I would have 5 times 0, which is 0, and 5 times 1 is 5. Now I add together. 7 plus 0 is 7. 0 plus 5 is 5. Like that. Okay? So the 1, 0 and the 0, 1 allow me to represent any two-dimensional vector. Okay? So we can express any two-dimensional vector using these two vectors. One, 0, and 0, 1. Okay? Any two-dimensional vector using 1, 0, and 0, 1. Okay? So these vectors (1, 0, and 0, 1) form a basis for the plane. Okay, and let's have an example of that here. Okay, so for example, this would be the point 1, 0. Okay, this would be the point 0, 1. Okay, so 1, 0 means 1 in x and 0 in y, so that's this one here. Okay, and now I can represent any vector using 1, 0 to describe its left and right, and 0, 1 to describe its up and down. Okay, and that's the idea of a basis vector. Okay, so this is my plane here, and we're always going to assume that the basis has a right angle. Okay, that's not necessary. You can have bases which don't have right angles. This is completely fine to do so, but it's not as nice, and we'd like to have everything behave as nicely as possible. And when you have directions that are at right angles to each other, you end up with the nicest possible situation. Okay. So that's a basis for 2 dimensions. Okay. In 3 dimensions, we have um, 1, 0, 0. We have 0, 1, 0. And we have 0, 0, 1. Okay? And this one allows me to handle every first component. This one allows me to handle every second component. And this one allows me to handle every third component. Okay? And we give these names. Okay? We call this one I. We call this one J. And we call this one K. And I'll give them a little arrow on top just to say that they're vectors and not scalar numbers. Okay? Okay. I, J, and K. And you might say, well, why would we do this? And one reason for this is that it allows us to compress notation down. So we'll have an example here. Okay, say we have 3, minus 2, and 4. Okay. Well, that takes up 3 lines. Okay, it's quite a big thing. And I can express this instead as 3 times 1, 0, 0, plus minus 2 times, or just minus 2 times 0, 1, 0, and then plus 4 times 0, 0, 1. Okay? And now from here, it's very, very simple just to change their names to these other vectors, and I end up with 3 times the I, plus minus 2 times the J, and then plus 4 times the K, like that. Okay, so I end up with something which fits on 1 line instead of having to use 3 lines. Okay, which is one of the main reasons we do this. Okay, so that is the end of this notebook. I'll grab another one here in a moment. I'm just going to pause for a second. Okay, so I just grabbed a new notebook there. So for any 3D vector, we would have x, y, and z. Those would be the different components. Okay, this would be x times the I vector plus y times the j vector, and then z times the k vector, like that. Okay, which is the basic formula, and this formula appears on page. Well, the notes here they don't start at 1. They start at page 1, so 65 is the page in the notes. Okay, and this allows me to just take up 1 line. Okay, and we assume that these 3 vectors, I, j, and k, exist in a 3-dimensional So we have kind of a three-dimensional one here. This would be my x-plane. This would be my y here lying flat. And then my z is up and down. Okay. And I'll mark these in different colors. So the vector that goes in the x direction with length 1, that's I. Okay. I have a little arrow. Okay. The one that goes in the y direction, in the positive direction with length 1, that's the j vector. Okay. And the one that goes in the z direction, okay, with length 1, is the k vector. Like that. Okay. And I can get everything in terms of those if I want to. Okay. In 2 dimensions, if we know we have 2 dimensions, we still can sometimes use I and j, but people are a little bit less hesitant to use 2 lines than they are to use 3 lines. So often you'll just see 2-dimensional vectors represented as 2-dimensional vectors. Okay, so in 2D, we would have that xy would be equal to x times what's called an I vector. I just means the vector in the x direction. And then y times j, like that, okay? Where I is 1, 0, and j is 0, 1. Sorry about my j's, by the way. I know they're not very good. Okay, so that's I, j, and k notation. Okay, we've talked about how to add them together. Okay, let's see how to add them together using I, j, and k notation. Okay, so let's have 3, 1, 4 plus 2, 0, 5. Why not? Okay. So the first thing I'm going to do is change these to I, j, and k expressions. Well, what's this equal to? Well, the first term here is 3 times I plus 1 times j, which I'm just going to write as j. Okay, and then 4 times like that. So that's my first term. Okay, and now I'm going to add on my second term, which is 2i and no j's, 0j, and then I have 5k's. Like that. Okay. And of course, this is not difficult to do. At this stage, they just look like variables, okay? Which is very easy to solve. Okay. What do I end up with? I would have 3 plus 2i. I would have 3 plus 2 times the I. I would have j plus 0j. So that's 1 plus 0 times j, and I would have 4 plus 5k. And what do I end up with then? That's 5i plus 1 times j, okay, plus 9 times k, and then that gives me what? 5, 1, and 9, like that. Okay, so that's the I, j, and k notation. Okay, and of course scaling is also very simple. let's say I have the vector 2, 1, 4. And I want to multiply that by 3. Okay, well then that would be 3 times, and I'm going to change this vector into the I, j, and k notation. So this is 2i plus a j, 1 times j, and I have 4 times k, like that. It's very easy for me to finish this off now. Okay, what is this? 3 times 2 gives me 6 i's. 3 times 1 gives me 3 j's. And 3 times 4 gives me 12 k's. Like that. And if we want to convert back, it's of course very simple to do so. I end up with 6, 3, and 12, like that. But that takes up 3 lines, which, you know, is not a waste of space, but it takes up quite a lot of space. Okay. So that's addition, that's scalar multiplication, and the IJK notation. And now we'll talk about something which is very important actually, and that's the zero vector. Okay. And anytime you have addition, you need something which behaves like 0 in order to get a useful system. Okay, so what does that look like? Okay, well, very simply, the 0 vector is a vector of all zeros. Okay, it's very simple, and it has a special property. Okay, we'll do it in 2 dimensions. In 2D, okay, we use this notation, 0 with an arrow. The arrow indicates that it's a vector. Okay, then we'll add on some vector, which we'll call v, okay? And it will always be the same thing as v, and it's always the same thing as adding the 0, 1 on the other side. Okay, doesn't really matter. So let's have a look here. If I had 0 and 0, and I added that to v1, which is the first component, v2, which is the second component, well, that's the same thing as v1 and v2, which is the same thing as adding the 0 on the other side. Okay, so the 0 vector is a vector I can add on, and it doesn't change anything. Okay. Okay. And the 0 vector has one other important property, which is that any scalar multiple, of the 0 vector is the 0 vector. Let's have a look at that. Let's say I take some number. Oh, let's take an actual number. Let's take the number 6. Okay, I'm going to multiply that by 0, 0 in 2 dimensions, and what do I end up with? Well, then I would have 6 times 0 and 6 times 0. Okay, which is of course 0. 6 times 0, 0, and 6 times 0 is 0. So I just end up with the 0 vector again, okay, which is very simple, but also very important that I have that kind of information. Okay. Okay, so that's quite a lot to get covered in a day. Okay, so I'm going to stop here, and then we'll move on the next day and do a bit more from the vector section. And if you have any questions, of course, you can post them in the comment sections, and I'll do my best to get back to you all. Okay, thanks everyone. Bye.